Okay, now solving systems with matrices is very similar to solving by elimination. It's just we're going to rewrite everything, kind of keep it in a more organized way by using matrices. So a reminder, the elementary row operations are that you can interchange any two rows, you can multiply rows by non-zero constants, and you can add rows to each other. So the goal is to do these elementary row operations that are checkmarked above to get our coefficient matrix in row-echelon form, which looks like that. Now, row-echelon form is similar to reduced row-echelon form. Reduced row-echelon form is when you have zeros here, and then the diagonal of ones, and these are all zeros. So if that were the case, you don't have to do any more work to see what x, y, and z are equal. But in this case, if this represented a system of equations, this is like having a system in triangular form where you know like z is equal to 6 from this bottom row, and then from the second row you see, alright, y minus z is equal to 4, so then you could plug 6 into there to figure out what y is. Then once you know y, you could take this top row, which represents the equation x minus 2y plus z equals 5. Alright, plug z into there, whatever you got for y into there, and then solve for x. Alright, so once you have it in row-echelon form, you can use back substitution to solve. So let's try two examples and also see how the calculator could do this for us. So in this first example, we have a system of equations. So first thing we want to do is write it as an augmented matrix. So that would look like this, a 2 by 3 matrix, where the first row is 1, 7, 0. Right, so 1x plus 7y equals 0. That's where those numbers come from. Alright, and then 2, negative 8, and 22. Okay, now we can use Gaussian elimination to rewrite the matrix in row-echelon form. Alright, so if I call this equation 1 and that equation 2, I could get a new matrix by leaving the top row as it is, and then the bottom row is going to be negative 2 times the top row plus the bottom row. And I'm going to do that to eliminate my x's. Alright, so negative 2 times 1 gives us negative 2, and then when we add that to 2, we get 0. Alright, and then negative 2 times 7 is negative 14. When we add that to negative 8, we get negative 22. And then 0 times negative 2 is 0. Add that, and we get 22. Sorry. Alright, then we could multiply everything in the bottom row by 1 over negative 22, or like divide everything by negative 22. Alright, and then, that would be our new matrix after just taking this bottom row and dividing everything by negative 22. Alright, so now this is in row-echelon form, so we can see that, alright, x plus 7y is equal to 0, and also y is equal to negative 1. Alright, so once we plug negative 1 into there, we get x minus 7 equals 0, so we get x is 7. Alright, so that would be our solution to the system, 7, 1. Now let's see how we could do that with a calculator. So if we open up the calculator, what we're going to do is open up a new calculator. So go to the home screen, new document, add a calculator. Alright, for row-echelon form, we're going to type in REF with parentheses. Then, with the button next to the 9, we can choose one of these options to get a matrix. This 3 by 3 option here will let you edit the number of rows and columns. Alright, then you're going to type the augmented matrix in, which I'm going to pause and do right now. Okay, so once you type that in, you get this for your, this is just row-echelon form. Alright, so that tells you that x minus 4y is equal to 11, and y is equal to negative 1, which is what we got. I mean, they did it slightly differently, but this is going to lead you to the same answer. Alright, and then for reduced row-echelon form, you do the same thing, but you just do RREF, and it'll reduce it down to get that identity matrix, so you can get the same answer that we got, x equals 7 and y equals negative 1. Okay, and then I just checked this on the calculator here just to make sure we got the same answer, and then we did. Alright, so you might be wondering, like, why would I need to use this if the calculator could do it? Well, for solving systems, you don't need matrices, but it's good to know how to use matrices to solve systems, because matrices are used in different upper level types of maths, and the stuff we learn later with matrices will make more sense if you kind of understand this context.